everyone. My name is Thales West. I work here for Scion. And today I would like to show you some of the results from a work we have been recently developing here, looking at forestry, climate change, and risk. And here we have it. So specifically, I would like to talk to you about a work that we call diversification of forestry portfolios for climate change and market risk mitigation in New Zealand. Okay, so we know that climate change will affect forestry in New Zealand. Here we just have two figures as examples of how precipitation and temperature will change, and we know that those changes will affect productivity, right? So there is a need to mitigate future risks imposed by climate change to forestry investments. How do we propose to do that? Well, with investment diversification, right? So any type of investment is arguably associated with an expected level of returns and an expected risk. Diversification reduces the exposure to risk, and a common path towards diversification is to reduce risk by investing in a variety of assets, okay? And that is called portfolio. Just as an example, that's exactly how the KiwiSaver works. All right, so how do we construct an optimal portfolio? Here we have an example of a stock, right? This is one stock that you can buy from the stock market. What you see here is a time series of the price of this particular stock, right? So from this type of information, this time series information, you can obtain information about risk or volatility, and you can also obtain information about returns over time. Okay, and an optimal portfolio is the portfolio that maximizes the expected return for a given amount of risk, or that minimizes risk for a given expected target return. Okay, and I'm highlighting minimizes because here in this work, we constructed two types of portfolios. One is called low target return, forestry portfolios. The other type is called high target return forestry portfolios, and all of them are based on a minimization problem once we set up a given level of return. Okay, but how our forestry portfolios look like? What are those forest portfolios that I'm talking about? Okay, well, first thing is that we're not looking at prices per se, but we're looking at annualized forestry returns. So we have a time series for that, okay? And these returns, they're just annualized net present values of the forest plantation that we're gonna simulate here. So we're talking about dollars per hectare per year, okay? We are also talking here about climate change, so we're talking about the future, right? So to be able to simulate these returns into the future, we obviously need to apply some simulation methods. And our simulations are basically based on two components. One is the future forest productivity under climate change scenarios. We're talking about log volumes per hectare, as well as future log prices. So price per log. Okay, we're gonna put all this information together in order to construct this annualized forestry returns time series, and then we're gonna use them to construct the portfolios. Specifically, the steps that we took here were, first, we simulate future climate scenarios for 2020 to 2090, and the scenarios are based on 6 global climate models, and these models consider two types of climate change scenarios called RCPs, okay? And here I'm gonna show you the results for RCP 2.6 and 8.5, and basically what we have here is that with RCP 2.6, we have a slightly warmer planet, with RCP 8.5, we have a much warmer planet. Okay, we're going to use the output from these 6 climate models to simulate future forest growth. We're talking about Pinus radiata regimes here, using the forest growth model called 3PG. Okay, we're also going to forecast log prices for 2020 to 2090, and those forecasts are based on projections from this model called Global Timber Model, along with historical log prices from New Zealand. And finally, we combine these pieces of information to compute the annualized forestry returns. And then we use that information to construct our so-called forestry portfolios. Okay. So let me show you some of the results that we have. In terms of the future climate scenarios, specifically for our study site, which is located north of Christchurch, here is how our climate variables that we used in 3PG look like, okay? Again, we have the two different RCPs here. We have climate variables such as rain, sub-zero days, maximum and minimum temperature, okay? And of course, we have in each panel 6 different lines. They come from the 6 different climate models that we used, okay? So we are using this information to simulate forest growth with 3PG. And here is an example of how 3PG simulates forest growth, okay? Here we have a forest that is planted in 2020, harvested in 2050. What is really important for us is the volume at harvest, because that is the volume that has value. We have 6 growth paths here, and they all come from the 6 different climate model data, all right? And we also simulate growth for 2 different Pinus radiata regimes. One is the T7S300, where we have thinning at age 7 and final stocking of 300. And the other regime is 79S600, where thinning happens at age 9 and our final stocking is 600. Okay. All right. So if we simulate these volumes of harvest here for each year and plot them from 2050 to 2090, this is how they look like, okay? Again, we have the RCPs here, we have the 2 regimes, and we have 6 lines in each panel corresponding to the data from the 6 climate models. So what we did was we created averages based on these 6 different lines in each panel. And we constructed confidence intervals along these averages, okay? And we used this information to create a high, average, and low forest productivity scenarios, okay? So keep those in mind. We have 3 different forest productivity scenarios. We're gonna work with them. Our portfolios are gonna be based on them, okay? But we also need to know the log rate volumes associated with these volumes at harvest, right? Because those are the volumes that actually have value. How do we do that? Well, we go from volumes at harvest to log rate volumes, considering these 6 different grades here, by multiplying the wood volumes at harvest by the log grade percentage from this table here. And because we can play with these different percentage, we can actually go from 2 regimes to 4 regimes, having each of our original regimes under pruned and unpruned versions, okay? But we still need to know the future log grade prices. How do we do that? Well, we adopt some projections from this so-called global timber model, along with some volatility that we extract from historical log price data for New Zealand. And we combine all this information into some Monte Carlo simulations. And then this is what we have for the 2 RCPs, okay? So here we have the historical data, and here we have the projections after 2020. And again, because we have different ranges here, we can use them to create high, average, and low log prices scenarios. In this example, we have those scenarios for P1, okay? All right. Now, all we need to do is to combine the log price scenarios and the log volume scenarios to create the annualized forestry returns that we're going to use in our portfolio analysis, okay? So how do we do that? We basically multiply the log rate volumes by their prices, sum them up, and annualize them. And then we have the annualized forestry returns here. Okay? So again, we have the two different RCPs, we have our 4 different regimes, and in each panel, we have a line or a time series that corresponds to any specific scenario. Okay? We are going to construct one forestry portfolio per scenario and per RCP. And looking at the scenarios here, you can see that we have low average and high log prices combined with low average and high productivity scenarios, okay? Looking at this at once, it might be a bit overwhelming, right? So let's just focus, for the sake of an example, on one specific scenario, okay? Under one specific RCP. For example, high log price scenario, high productivity scenario under ICP 8.5. So here, what we have highlighted in green is 4 time series for the 4 different regimes. And we're gonna look at this time series here, and we're gonna extract some information from them associated with returns and risks. And based on those returns and risks, we're gonna construct our portfolios, okay? And here is our results, our portfolio results, here for the low target return portfolio, okay? Each bar here that you can see is an independent portfolio, but let me just walk you through this graph. What we have here is the log rate scenarios, low, median, and high, versus the forced productivity scenarios, high, median, and low, for the 2 different RCPs. So depending where you are across these scenarios, this range of scenarios, you have an optimal portfolio based on our low target return objective, okay? If we change the objective of our portfolio, if we go from the low target return to a high target return, then our portfolio also changes, okay? And in this case, we started to see the presence of the T7S300 prune regime, which is, according to the data that we used, associated with the highest returns, but also with the highest risks, okay? So here we have just 2 examples of our portfolios. Okay, and with that, let me move into the conclusions and future research directions. Well, our results suggest that regime diversification can reduce climate change and market risks. Okay, but this presentation is really about the framework that we are proposing here, how to create these forestry portfolios, not the results per se. Okay, we can apply this framework based on input from forest managers, different input, different assumptions, okay? For example, we can consider different regimes. We could also examine different tree species as part of portfolio options. Right now, we're only focused on Pinus radiata. We can also consider other sources of risks, for example, future diseases or forest fires. And we can expand our analysis to other sites or other regions. Okay, and that's all I have for you. Thank you very much.